A study of this crossing indicates a large hydraulic force due to momentum of flow was directed at the abutment. Future damage can be expected with these flow conditions. In modern highway design, the surface waters cannot be neglected. The increased cost of drainage facilities makes it imperative that good hydraulic design be used. On the road surface, the cross slope must be sufficient to get the water off. The paved surface must have sufficient cross slope to prevent ponding of water in order to maintain large volumes of vehicular movement without interruption. The curb and gutter designs must include adequate provisions to collect and dispose of the surface water. Otherwise, ponding can cause serious traffic delays. The road shoulders must have adequate slope to pass the water from the paved surface into roadside ditches and eventually into the natural waterways. Many drainage channels are crossed by highway systems, which involve the highway engineer in the design of many structures such as culverts and bridges. Whatever hydraulic structure he selects in crossing the natural drainage channel, he must follow the recognized hydraulic design principles. What are those principles? Open channel flow deals with flow of water in rivers, ditches, and flumes. Some of the principles involved in open channel flow can best be illustrated in the laboratory. To illustrate the principle of continuity, water is shown flowing through a contraction, which reduces the width of the channel. In the wide portion of the flume, upstream of the contraction, the flow is deep but slow. As the flow enters the contracted area, the depth or cross-section decreases but velocity increases. The quantity of water passing the deep section is equal to the quantity passing the shallow section. This is known as the principle of continuity. Now let's go through the whole operation. Flow through a contraction by adding dye to the flow. Notice the acceleration of the flow at the contraction. And there you have it, proof of what all engineers should know, but many fail to consider. The volume of water passing any cross-section in a given period of time is constant. In other words, depth of a flow decreases while the velocity increases past a contraction. If a wide channel suddenly becomes narrow, in this case contracted from the bottom and side, the velocity increases. The water has to pick up speed in order to get the given volume past a point in a given period of time. Now let's examine the basic energy principle in a straight rectangular channel contracting to a smaller rectangular channel. The total energy at a cross-section of flow is the sum of all the potential energy and kinetic energy at that point. The potential energy due to elevation of the bed of the watercourse is measured from some horizontal datum, shown here as a line of zero elevation. It is known as elevation head, or simply elevation. The potential energy due to pressure is known as the pressure head, which is represented by the depth in open channel flow. The kinetic energy due to motion is known as the velocity head and is measured here by the use of a pitot tube placed in the flow. The height of rise in the pitot tube above the normal water surface is velocity head. The sum of all three of these components of energy is known as the total head or total energy. As the water flows through the contraction, the depth decreases and the velocity head increases. Also, the flow loses energy because of the work it does in overcoming the resistance offered by the channel between the two sections. After the water travels over a certain distance in the channel, the resistance causes a lowering of the total head. The total head is the sum of elevation depth of flow, and velocity head. The basic energy principle states that the total energy or total head at one section of the flow is different from the total head at a point downstream by the amount of energy lost through resistance to the flow between the 2 points. This total energy loss is known as the head loss, denoted here by the orange bar. It is another very important concept to be taken into consideration in designing for open channel flow along highways. A special application of the total head is specific head. By definition, specific head is the sum of velocity head and depth of flow. When the specific head is plotted against the depth of flow, a useful curve known as the specific head diagram is obtained. The ordinate is specific head in feet, and the abscissa is depth of flow in feet. The curve is made for constant discharge in the rectangular flume. It illustrates the 2 depths of flow which can occur with a given specific energy depending on slope and roughness of the given channel. To illustrate the construction of a specific head diagram, consider a rectangular flume with a constant discharge. For a mild or flat slope, the flow is deep and, as shown by the pitot tube, has little kinetic energy. Placing a specific head grid upon the flow, one can then determine the energy point defining the flow. This is accomplished by finding the intersection of the depth of flow and depth of flow plus velocity head, remembering that depth of flow plus velocity head is specific head. This represents one condition of flow. A steeper slope produces a decrease in depth of flow. The kinetic energy has increased only a small amount with nearly a 50% decrease in depth. This point locates on the specific head diagram as depth of flow and the intersection of specific head. The rise in the pitot tube above normal water surface is velocity head, as shown by the dashed line. A further increase in slope produces a point of minimum energy. Locating this point, you will observe that the kinetic energy is 1/2 the depth of flow, which will be true for any rectangular channel at the point of critical depth and critical velocity. At depths greater than this, the flow is at subcritical velocity and has relatively low kinetic energy. By further steepening the slope, we obtain depths less than critical depth and supercritical velocities of high kinetic energy. In the construction of the point describing the flow on the specific head curve, the depth of flow is relatively small. The specific head is large. With further increase in slope, the depth decreases very little. Locating the point on the specific head diagram, the depth remains nearly the same. However, the kinetic energy represented by the distance from the sloping straight line and the point on the curve increased tremendously, resulting in a large specific head. We now have 5 points that define the specific head diagram. On this curve, one can read the specific head for any depth of flow. As depth occurs in both the ordinate and abscissa scales, the line of equal depth gives one limiting boundary to the curve. The minimum point on the curve locates the position of critical depth and critical velocity head. Depths of flow greater than critical depth are at subcritical velocity. Depths of flow less than critical depth are at supercritical velocity. Understanding of the related flow phenomenon as depicted on the specific head diagram is essential to good hydraulic design. Now let's take a look at the energy principle using an OG spillway and demonstrate a common but valuable method for dissipating kinetic energy. Water is flowing on the left at subcritical velocity and very deep. As the water goes over the spillway, part of the potential energy due to depth and elevation is changed to kinetic energy. Below the spillway, depth is decreased considerably, while velocity is increased in accord with the principle of continuity. The velocity is increased to supercritical. When a high-velocity jet comes off a spillway as shown, a hydraulic jump will occur if there is sufficient depth of flow in the downstream channel to force the jump. The velocity below the jump is decreased while the depth is increased. Wise use of hydraulic principles to convert one type of energy to another, that is, putting the principles to work, will pay valuable dividends for engineers who must provide for proper design and maintenance of open channels along the roadways of the future. A hydraulic jump can be made to dissipate kinetic energy that might otherwise damage a channel. The characteristics of the jump can be calculated by use of the momentum equation. The momentum principle states that in order to change the velocity of a body, a force must be exerted on the body. The hydraulic jump is a case where the magnitude of the velocity is reduced, the force being supplied by the deep water downstream. When the channel conditions downstream are such that this force does not exist, the jump will not form. Too large a downstream force may cause the jump to move upstream. The stability of the jump depends on the downstream flow conditions. Let us again use a laboratory model to demonstrate momentum. In this case, a small curved rectangular channel to illustrate momentum of flow around bends. For a low discharge on this slope, the channel will contain the flow. At the bends, we have flow separating from the boundaries and climbing of the outside wall. In fact, momentum carries the flow on the outside of the bend to a height several times the approach depth of flow. On the inside of the bend, the flow separation is such that even the bottom of the channel is exposed. An increase of discharge on this slope would cause overtopping of the walls, and in a field installation, severe damage could occur. The importance of understanding momentum in design is again illustrated by an increase in discharge on this mild slope. The use of super elevation at bends or increased wall heights are necessary to supply the force to change the direction of momentum of flow. The understanding of momentum is essential whether one designs in the subcritical or supercritical flow range. Momentum carries the flow to the outside of the bend. The boards on the wall are a field expedient to produce a force to offset momentum and maintain capacity of the channel. A grate inlet is an illustration of a structure in which momentum plays a major role. Note that the bars in the inlet are parallel to the direction of the flow. In the laboratory, the operation of this type of grate inlet can be demonstrated in a qualitative way to show some of the factors which affect the flow through the inlet. By observing the depth of flow downstream of the inlet, one can judge the efficiency of the inlet. The length of this grate is 3 times the width of the flume. Changes will be made to show the effect of slope and the resulting increase in momentum on the amount of flow getting by the inlet. For the 1% slope, all the flow is carried into the inlet. The jet of water is split by the crossbars dividing the grate into parts. On a 10% slope, a large percent of the flow gets past the inlet and continues down the flume. Although these tests bear no quantitative comparison to an actual storm inlet, they illustrate the point that on a steep slope, the water has more momentum and tends to skim over the grate inlet. The bars in this field installation are perpendicular to the direction of flow. In the laboratory, the efficiency of this type inlet can be illustrated by placing the bars crosswise to the flow and observing the flow passing the inlet. Here on a 1% slope, most of the flow is intercepted, but more of the inlet is being used. Each opening intercepts a separate jet of water. As the slope is increased to 3%, some of the flow bypasses the inlet. And with a 10% slope, the inlet intercepts less flow. The momentum causes the water to glide over the bars and continue downstream. This shows that the direction of the bars is important, especially on steep grades. A curb opening inlet has momentum problems which are similar to the grate inlet. In the laboratory, the curb opening is demonstrated by a small rectangular channel with a removable side. The momentum of the flow, here on a 1% slope, must change direction both horizontally and vertically. Consequently, a good curb opening inlet is more difficult to design than a grate inlet. As the slope is increased from 1% to 10%, the amount of water going into the curb opening inlet is decreased considerably. Again, notice the flow going past the inlet. The length of the curb opening inlet is important because it takes some distance to change the direction of flow after the flow has acquired momentum. Here the opening is 3 times the width of the flume. And when the opening is changed to only 1 time the width of the flume on the same slope, the capacity to carry the flow is decreased by more than just a factor of 3. Proper gutter cross slope and length of opening are factors in design. The effectiveness of an inlet also depends on how it is placed. Even a long curb opening is inefficient if the water doesn't get to it. As you can see, the poor gutter design makes this inlet ineffective. The water will eventually overload another inlet further down the system. When an inlet is placed where the water must go around a corner to be intercepted, ponding can be expected. Again, the principle of changing the direction of momentum is involved. As the volume of flow increases, momentum increases and more ponding occurs. As the discharge is increased on this 4-foot depressed inlet, a maximum efficiency for this cross slope is obtained. Further increase in discharge and flow goes by the inlet. Again, we see the effect of the momentum of flow in design. These examples illustrate problems in which the momentum principle is a major factor and must be considered in the design. In fact, there must be a careful consideration of all the hydraulics principles. The principles of continuity, energy, and momentum cannot be violated. Water will develop sufficient energy to carry itself through a contraction. If the contraction is too small for the amount of energy present, the water will accumulate upstream from the contraction until it has built up enough potential energy to provide the force necessary to accelerate the flow through the contraction. The proper use of open channel flow principles in the hydraulic design of bridges, culverts, channels, and similar hydraulic structures will provide safer and more economical highway design. The designer will consider size of ice and debris likely to be encountered at flood time and design accordingly. The impact of ice or debris and the static and kinetic forces of water can be very large. The channel's slope, the lining, and the shape all have their effect on the depth and velocity of flow and must be considered in the hydraulic design of open channels. Whether one deals with the hydraulic problems on mountain roads with extreme steep slopes or in rolling flatlands, the principles of hydraulics are the same. The problem of handling the surface water in highway design is indeed important. Therefore, an understanding of the fundamental principles of flow is necessary to adequately design and maintain the highway network.